So what exactly we study here? So we study something called static electric field, and the way it is generated is definitely due to the static charges. So what we study is static electric field, and the one which creates it is the static charges. So in a way, you can say we talk about or we study about the charges at rest in a way, but this branch of physics actually deals with the static electric field, which in turn is created by static charges. And a charge will be static, will be frame dependent. So there are multiple layers of it. First layer is we study about static electric field. The second question is it is generally developed by the static charges, and the static charges comes with respect to some frame of reference. Later on, when you will go for the higher studies, we have the Einstein theory of relativity, and we have something called the Lorentz transformation, which talks about the change of electric field by virtue of motion, by virtue of change of frame of reference, in which the same electric field will appear differently if you change the frame. Okay, so moving frame will give you different answer, and the frame at rest will give you different answer. The answers will not be same, but that is of course beyond as of now present discussion. In magnetism, I will introduce a bit about it in detail. In this particular chapter, we are not supposed to bother about the Lorentz transformation kind of thing. Why I said this? Because you need to remember that it is not something very much well defined everywhere. It is frame dependent definitions. So this chapter having inherently a frame which is the ground frame, which we don't mention explicitly, and we also believe that the charge in that frame is at rest. Okay, so this is what we start with, the thinking process. So the definition of electrostatics, you can say like this. So what we can write? It's a branch of physics in which we study about static electric field. So it's a branch of physics in which we study about the static electric field. Generally, static fields is developed by static charges. Okay. So that's the basic thing about this naming convention. What we mean by the electrostatics. So it's a branch of physics in which we study about the static electric field, and who creates it? Charges at rest. Okay. So the big question is, what do you mean by charge? What is charge? Anybody? What is charge? Am I audible, guys? Anybody can tell me what is charge? Whatever you know, you can just tell me. I mean, it really doesn't matter whether you know it correctly or inaccurately. It doesn't matter. What is your perception about charge so far?
Charge is something which is related to the electrical changes, I think.
Of course, that's correct only. There's nothing is wrong about it. What you said is correct. But we are trying to understand what exactly is charge. Can we see it?
No.
Can we experience it? So what we can do then? If we don't see or experience, then what we can? How we are going to understand what is charge?
Sir, charge travels in packets.
No, charge never travels in packet.
No, no, like no, sorry, I got confused.
Kanu, you want to say something?
Like when electron is present, there is negative, and when it is not there, it is positive.
But you're talking about electron, but I'm asking about charge, because charge, I think or I believe, is more fundamental than a particle carrying it, right? So electron happens to be a particle which carries, fortunately. There are others also. So they are some lucky guys. The God has gifted them with something extra. So my fundamental question is, what is charge itself? Not what is carried by electron or proton or some alpha or something beta. So our discussion right now is only about the charge, because learning charge is very, very important to decode the entire, you can say, electromagnetism, and to understand the universe, to understand ourselves, to understand your heartbeat, to understand the life. That's most fundamental. Okay, so let me tell you guys. Charge is something very fundamental characteristic possessed by matter. Yes, what you heard is right. It's the most fundamental characteristic. Can we see character? No, we can't see character, whether it's a good character, bad character. We talk in a very literal sense. We cannot talk about character. The question is, if we cannot talk about character, then how will understand the character? The answer is through your actions, the way you behave, the way you interact, the way we as an individual interact with each other reveals our character. Similarly, if a particle having a character called charge, when it will interact with any other charge particle, the character will be manifested by the action. Now the question is, what are the type of actions here? The answer is attraction or repulsion. In the world of charge particle, there are just two actions, attraction and repulsion. The action you can also call interaction. And what makes this interaction possible? The possibility is called charge. What makes this possible exactly is called charge. Interaction, yeah, you heard it right. For example, if you want to talk to a person from a foreign country who doesn't speak your native language, how will you interact? You cannot interact until there is something common language. So let's say you and the person can speak French. The person was from France. The interaction is possible, isn't it? But imagine yourself, you know your own language, he knows his own language, and there's nothing common. Is it possible for interaction to take place?
No.
The answer is no. Similarly, when two particles interact, either they attract or they repel, then what makes the interaction possible is something common characteristic. They must have something common. And this something common we call charge. Of course, you cannot see it. You can only realize it through action, through interaction, through attraction, through repulsion. So in nature, God has given just two fundamental characteristics to every particle in this universe. And what are these two fundamental characteristics? One we just talked about called charge, and the other will be, what is the most fundamental characteristic? And the answer is mass. Mass is again a character. Of course, you cannot see it, but it is this character which let you interact with any other body or particle having mass. So mass interacts with other mass. So when two masses or when two particles interact by virtue of gravitation, what actually interact is the mass as a character which is common to both the particles. For example, if Earth is interacting with moon, or if the sun is interacting with Earth, they must have something common. And what is that thing? That thing which is common? The common property, what we name it? What is common between the moon and the Earth? Sun and the moon? What is common? Am I audible, guys?
Yes.
So what is common between the Earth and the moon? Both have mass. The mass is the character, the fundamental character which is common to Earth also, which is common to moon also, and it enables them to interact. It's like a language in which they can talk to each other. So how the charged particles talk to each other? Through a common language, and the language is called charge. Charge is the language, and definitely you cannot see it. Can we create charge? Can we
No,
create
sir.
character?
No.
No. It is impossible to create character. Character is always born with you, you have inherently. The only thing you can do is you can manifest it. And how you manifest? Through interaction. So the reverse way of saying is the interaction is facilitated through some fundamental characteristic between matter, and out of two fundamental characteristics which let them interact, one is charge, another is mass. If you ask me which one is more fundamental, I can tell mass is more fundamental. Why? Because the nature has created a mass without charge, but the reverse is not found yet. So we cannot have a charge without mass, but we can have mass without charge. So you may say, like example, neutron. So neutron is having mass, yes, but the neutron is not having
Charge.
charge. But if you go deeper into science, the philosophy becomes wrong. There is nothing in the world which is having zero charge and zero mass. Okay. So neutron is having charge actually. I will explain in a while. So neutron is having charge, but equal plus and equal minus. And because of the equality of plus and minus charge, the net charge is zero. But that is the second level of fundamental. Like, of course, we are talking about the JEE level, and here we do not say that neutron is also made of something called quarks. So I will talk in a small detail about quarks before we go back to the discussion of electrostatics. So if I want to define charge, how I'm going to define? It is the one of the most fundamental characteristic of a matter by virtue of which it can interact with any other particle having similar characteristic. So a charge can only interact with the charge. So when you bring a proton in the vicinity of neutron, will they interact? Yes or no? Will they interact?
No.
So of course they can interact, but with the common property of mass.
Yes.
So gravitational interaction is possible, but can we have the electrostatic interaction possible in that case?
No.
The answer is no. And what you need to realize that these two interactions are totally independent of each other. So your gravitational interaction with the mass character and your electrostatic interaction because of your charge character are two different and independent phenomena. A charge can exhibit both interaction at the same time. Totally possible. The only problem is comparing or compared to the electrostatic force, the gravitational force stands nowhere. And that is why generally the gravitational force is only experienced by the heavenly bodies in a significant manner. For tiny objects, this interaction is so small that it essentially it looks like there is no interaction. So even right away, you are interacting with the benches, table, sofa, chair, ceiling fan, everything. But are you feeling it? The answer is mostly no. But you can easily feel the gravity. How? Try to jump or try to, if you're sitting on your chair, try to lift yourself. It's not very easy. Some effort is required because gravity is always working there. Which gravity? Of course, the Earth creates tremendous gravity because Earth is not a tiny particle. It's a humongous object. It's a heavenly body. And because of the size, you can say its gravitational efficiency or power or strength is good enough to be felt by us. So we are able to interact with Earth quite significantly compared to we are interacting with each other and experiencing that gravitational force is almost next to zero. So in our day-to-day life, we do not feel the gravitational effect. Charge is very powerful. A tiny charge can be very effective. So we'll talk about the ratio of electrostatic force and gravitational force. And to understand the order, how big is this? This goes to 10 to the power 40 to 42. This number is beyond imagination. It's such a huge number. So compared to electrostatic force, gravitational is negligible. In case of elementary particles, if we talk about the, let's say, two electrons and we try to find their force, we can get this order. So now time is right to write the definition about charge. What should I write here about charge?
It is a fundamental character.
So it is one of the most fundamental characteristic of matter by virtue of which it can interact with any other particle, or you can say bodies having same character. So charge is the enabler, it's a communication. Okay. So there are two ways to communicate between the inert object. How they communicate? They communicate through charge and mass. Okay. Later on, you will realize that the pumping of heart is a dipole-dipole interaction. The heart of a human body is the biggest dipole, and the way it shrinks and expands is due to the interaction of the charges. At a tissue level, you will come to know that it is creating charge, and these charges are attracting and repelling. That's how the pumping is naturally generated. The same thing goes with the digestion process of intestine. The intestine shrinks at one place and expands at other place, and creating a rhythmic fashion motion. This rhythmic motion is created by the quite rhythmic distribution of charge, discharging and charging process. Most of the human activity, whether it's a motor cell, is governed by the charge. Whether it's movement of hand, you may think that you are moving, but no. It is the charge which is communicating with each other, how to attract and how to shrink, and that's how this communication, the brain is able to control the charge movement in such an effective manner that you can maneuver your hand the way you want. So at microscopic level, everything is governed by only two fundamental things: charge and mass. Your brain, your memory, everything is just the manifestation of charge. What you remember, what you don't remember is nothing but the charge. The charge which the synapses stores, the neurons contains, the DNA information itself is the charge in a certain pattern, of course. So everything which has existed ever, having some brain, having some intellect, is possible because of the charge. It's powerful thing. And the God has given luckily just two fundamental characteristics which govern the entire universe. And so far we have been able to connect most of the dots, except that we're trying to still understand that can we connect this communication, these two characteristics together? Can we connect the charge and mass together? And this, the very idea to unify the theory of universe into single theory is known as the string theory, which you will just hear here and there, quite popular terminology. So the string theory is basically the approach to connect the most fundamental characteristic in nature. We still study charge separately and mass separately. The mass creates its own chapter called gravitational, and the charge is alone capable of creating everything else in the universe. So charge not only creates electrostatics, charge itself creates magnetism. Charge itself creates electromagnetic wave, and everything else in the world is EM wave. Right now, you're using this Zoom application to understand this, listen to this lecture, and everything is being transmitted at a very micro level. Some charge is oscillating to create the radiation pattern. Anyway, so we'll come to that. So charge is the most fundamental characteristic of matter by virtue of which it can interact with any other matter or particle having same character. Now we'll talk about something called experience. In how many ways charge can interact? The answer is there are two possible ways they can interact. So what are the possible ways they can interact? The answer is attraction and repulsion. Now this is experience, not something known in advance. We have experienced it over the time. Now because charge can exhibit two separate characteristics, attraction and repulsion, then there was a need to distinguish it, to make a clear distinction between these two phenomena. So what we did to make this possible? We created the notion of plus and minus charge. Is plus charge really plus? Is minus charge really minus? The answer is no. These are just assumptions, some sort of nomenclature. So I just told you by some name and because of the repeated literature and the usage and the consistency in the usage, it become part of our life. So we still feel that electron is negatively charged particle. Electron is assumed to be negative particle by some convention. There is nothing like negative and positive in the universe. Okay. The only thing which is real is charge, and these all are called assumptions. Okay. Now, when it comes to mass, have you heard about the mass repelling each other from your common experience? No. So, what you have heard from your common experience that mass only attract. So, what kind of interaction is possible between masses? The answer is only attractive. And because of the unitary nature of interaction, we never felt the need to define plus mass and minus mass. It could have been plus and minus, but luckily we only came across single type of interaction, and therefore the mass, which is also very fundamental, in fact one of the most fundamental characteristic, needs just only one representation. We call it mass. We never say plus or minus. I hope this is clear, guys.
Yes.
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 A strong force and weak forces are forces in nature, and of course they are fundamental. I'll talk about that. I mean, not generally talk about that in laws of motion, but I'll talk about again here. So charge is one of the most fundamental characteristic which enables various phenomena in the universe. One of them is definitely electrostatics. Later on in the next chapter, not next, I mean after a few chapters, we'll come across magnetism, which is due to the moving charges. So when charge move pretty much uniformly, what they create we call magnetic field. And when the charge accelerates or oscillates, then what they create we call electromagnetic wave. So all these things, whether it's a magnetism or electrostatics or the EM wave, are by virtue of charge, and therefore in the later part of development of science, we simply called electromagnetism as a single concept, because electricity and magnetism was studied as a distinct entity for quite a long time. But later on, after the discovery of atom and the discovery of quantum physics, everyone realized that these things are interrelated, and because everything is interrelated, so the birth of EM electromagnetism came into picture with a very famous Maxwell 4 equation describing it. So we'll also study the Maxwell 4 equation in the chapter of electromagnetic wave. Right now our interest is charge. I will be talking about charge and mass quite often together. The reason is the chapter of gravitation you are going to learn parallelly with electrostatics. So both chapters will be covered almost parallelly. Still, I will keep two extra lecture for gravitation, in which we talk about something which is not common. It is actually common, but still I will try to show you as a distinct entity because of some historical reason. So I hope the concept of charge is not clear because it's very deep. Even I'm trying to understand. But what is minimum you need to understand is that it is a characteristic you cannot see. It is the characteristic which enables them to make the interaction possible with something similar in nature. The reverse way of saying is if two parties are interacting and if the interaction is non-gravitational, then they must have something common, and that common we call what we call charge. So charge is the common factor, common characteristic, which was making this interaction possible. A very similar concept exists in thermodynamics. You might have heard about the zeroth law of thermodynamics, zeroth law, which says that if A is in thermal equilibrium with B, and if B is in thermal equilibrium with C, then A will be in thermal equilibrium with C. Anybody who has heard about this?
Yes,
Yes,
yes.
yes.
Zeroth law. It is quite intuitive, isn't it? A with A equals to B, B equals to C, and so A equals to C, right? But it is very deep actually. If you try to understand how deep it is, you will see the real worth of Zeroth law of thermodynamics. So what it is trying to say that if A is in thermodynamic equilibrium with a body B, and if B is also thermodynamic equilibrium with body C, then they must have attained something, a fundamentally something common, some common characteristic. And this common characteristic they realize and called temperature. So they said that because thermodynamically they are not exchanging energy, which means they are exchanging equally in both directions. That's why it's called thermodynamically. We don't use the word statically. There is nothing like thermostatically. What we use thermodynamically. Dynamic means the equilibrium is not static. The net change has stopped, but the exchange is happening. That's very interesting. So A is in thermodynamic equilibrium with B, which means A is giving some energy at the same rate as A is receiving from B, and vice versa. So the net exchange is zero. And that is why if A is in thermodynamic equilibrium with body B, so they must have attained something common. And that something which is common, we call temperature. Again, it's like a characteristic. Can we see it? The answer is no. We have defined it. Temperature is called characteristic, the fundamental characteristic. And because it was fundamental, but realized later on after the first law. So we wanted to put it before the first law because it was more fundamental, and we had no choice but to call zero. Understood? If we would have realized this before zero, I would have called this minus one law of thermodynamics. That's quite possible. Anyway, so this is how we study the fundamental ideas. So charge, we'll talk about charge. Charge interacts in two possible ways. Attraction and repulsion. Therefore, to distinguish so positive and negative charge is simply convention. So maybe I mean the electron was a minuscule particle, very small in nature, and they thought of it's a weak and they called it negative. I mean just maybe the thought process of that generation, the male scientist. Anyway, it doesn't matter. Now time has come to talk about more detailed thing about charge. So the most important fact, some properties of charge. So let's talk about first property. So charge is invariant. Have you heard this name? Charge is invariant. At the same time, I will tell mass is variant. What is variant? In physics, a quantity which remains same in every frame we call invariant. We talk about the inertial frame only. And inertial frames can be of two types: inertial frame at rest or inertial frame moving with constant velocity. Inertial means something which maintains the inertia, and inertia of rest or inertia of motion defines there are two types of frames. So anything, any quantity which remains constant in every inertial frame we call invariant. Not just charge and mass, there is one thing very fundamental which is also invariant, and that is time. Can we have the different measurement of time if you switch from one frame to other frame, or we
No.
will get the same answer? The answer is every
They-
frame you are going to get the same time measurement, and that led to the development of Galilean transformation, which you study in physics as a chapter called relative motion in class 11, very beginning. So the whole idea of relative motion actually emerged from the idea of the invariance of time, which was refuted by Einstein after the theory of relativity. He said, no, time is a variant. Every frame will not give you same time. And we came across a concept called time dilation. So of course, in classical physics, time is invariant, but in relativistic physics, time became variant. And that's why now we don't say time as a invariant. So the variance of time gives rise to the concept of Lorentz transformation. Just like the invariance makes the concept of Galilean transformation, the variance made it something called Lorentz transformation, which is a part of again relativistic physics. Not in our syllabus, we'll not talk much about. So mass is variant. Yeah, you heard it right. Mass is variant, and there is a very famous formula. What is the formula? The mass in inertial frame is m equals to rest mass upon under root of 1 minus v square by c square. Now this is the frame at rest. This is called rest mass, and this is what we call relativistic mass, which means the answer is not same in every frame. Understood? And therefore, the momentum will be how much? Momentum will be m into v of a particle having velocity. But m itself is okay. So what Einstein said? Einstein gave the very famous mass energy relation, if you remember. It is so famous that I expect that everyone knows.
E is equal to m.
mc square.
But m was the relativistic mass. This it was not m naught. So this becomes m naught. Now this is in terms of the rest mass. Let's square it both sides. We can write like this: 1 minus v square by c square. We can write like this. I hope. And you can see what is P square. So okay, I have to use this formula to make a very nice derivation. I will just show you, which will be very helpful to you for the atoms in nuclear chapter. So E square is this much. So what is P square? P square is m naught square V square upon 1 minus V square by C. So what is P square C square? That's interesting. Oh, we cannot like this. Yes.
Which is
So let's add this to relation. I want to add this. So what you can write here? M naught is okay. So this we can substitute, right? So 1 minus V square by C square. I mean, let's see. I mean, of course, we have to do something. Or we can simply say, that we can say, no, 1 minus V square by C square. Ah, that's fine. You can do it easily. So what we can do is we can rearrange P square minus P square V square by C square is M naught V square. So P square is how much? P square by C square. Am I correct? This is right. Plus, so we can take P square. Okay, this is, I want to take common actually.
V.
Yeah, I just am trying to make it common. So P square equals to P square plus M naught square C square into V square by C square, right? Yeah, now this is because I wanted to just substitute the V square by C square. So V square by C square is how much? That's so 1 minus V square by C square is 1 minus. Yeah, that will do my job. This will become how much? This turns out to be how much? This is correct. You can see. Let me know if there is some mistake in calculation. Something really challenging. Just a moment. No need to do this work. I'm just trying to develop the formula. So what I can write is E square from this equation. Let's call it equation 2. So 2 implies E square into, because 1 minus B square C square can multiply will upon P square plus M naught square equals to M naught square C M naught square C power 4, right? And so yeah. So what are we left with? If we cross multiply, E square equals to P square C square plus M naught square C power 4, right? Can you see this relation? So that energy square is how much? Momentum square C square. You can say PC whole square, or you can write the way you want. P square C square plus M naught C square whole square. Now this is a very famous relation called the Einstein energy relation. So E square is basically the momentum square, speed of light square plus M naught C square whole square. And what is m naught? The rest mass. This is a very famous part. I mean, equation. Why we need to know this equation? Okay, there must be some reason. So because E square is P square C square plus m naught C square whole square. In nature, we have two types of particles. Particles with zero rest mass. So we have particles. You can say for all particles with zero rest mass. For all particles with zero rest mass, that is when m naught equals to 0, we call them photons. So any particle with zero rest mass is called photons. The nature has decided that if you do not want to have mass, you must move with the maximum possible speed of the in the universe called the speed of light. And once you get mass, your speed will decrease. Anyway, so this equation will give you some answer. What if rest mass is 0? What we get? E square equals to only P square C square. The second term becomes 0, correct? And this gives the answer E equals to P. And from here comes the concept of momentum. So momentum is having a second definition, E by C. For which particle? Particle with zero rest mass, like photons. And that is the proof that even a massless particle can have momentum. What really matters is the energy. And from the Planck's equation, we know energy equals to h nu or sc by lambda. So momentum by definition is h e by c, which will give you the answer h by lambda, and that was the birth of the de Broglie relation, the matter waves, that lambda de Broglie equals to h by p. So I hope you must have seen these formulas. These are very popular formulas in chemistry when you study the atoms. And what you are seeing today is the derivation. What I'm trying to explain here, I'm trying to explain that no matter whether you have mass or not, even if your rest mass is 0, you may have momentum, and therefore every electromagnetic wave is capable of carrying some momentum, not just energy. They carry energy as well as momentum. And for EM wave, this is the formula of momentum, energy upon speed of light. There is a chapter in EM wave itself, it's called the radiation pressure. You need to know these formulas to derive it. Okay, so we'll talk about again in the chapter itself. So what I was trying to explain that the mass is a variant quantity. It is not same in every frame. What remains same in every frame is called the rest mass. And your perception of mass so far in your life was about rest mass, not about mass. There are variety of mass in nature. Okay. So we have rest mass, we have relativistic mass, we have gravitational mass, we have inertial mass. There are variety of mass. So okay, just to mention types of masses, you can see some mass. You saw rest mass. You saw what you saw? A relativistic mass. Then there is something called the gravitational mass. And what is gravitational mass? So the mass which appears in the Newton's law of gravitation formula. So when you write this formula, here the mass is trying to represent the attraction between two masses. So when mass is studied in the formula of Newton's law of gravitation, we call them gravitational mass. And then we have the inertial mass. So what is inertial mass? The mass that you study in the Newton's second law, F equals to ma, because this talks about the change of inertia now. Einstein proved later on that these masses are same. So he said the gravitational mass and inertial mass are not distinct quantity; they are same, and same as the rest mass. Okay. So of course the relativistic mass is different, and we also have some other mass. Among the rest, the most famous is called Bose Einstein condensate. So the Jagdish Chandra Bose sent a letter to Einstein when he was himself a PhD student and postdoc mostly, studying in the Dhaka University that time. And he was the only person from India who was translating German into English to spread the knowledge of science from Russia and Germany, of course. And he was so much influenced by the Einstein that he got the courage to write letter to himself and directly to him. That time, no one was able to talk to him. He was such a giant personality in the world. And Einstein got very much impressed with the work of this small kid because he was like a kid to him only. And the influence was so much that he named him for this discovery called the Bose-Einstein condensate. Of course, these are advanced topics not meant for us. Just for motivation purpose, I give all this information. Next. So we learned about charge. Charge is variant. Charge is
Sir,
invariant, but mass is variant. Yes.
sir, rest mass is invariant.
Yeah. Rest mass is invariant. The rest mass
And
is the. It's like what was your weight at the birth? Can we change it?
no,
Like whatever you have now, that doesn't matter, no?
yeah.
Your so the day you were born, whatever was the weight is the answer. That's fixed value. So rest mass is when you were not moving. How can I change it?
No.
Yes. It's a
And
definition.
all others are variant.
Yeah, of course. When you say mass, it's a relativistic one.
Okay.
Okay, you haven't understood this. Einstein tried to incorporate energy and mass into one single entity. So what he was trying to say that the universe is made of only one thing, energy. Okay, so let's say this is the universe. This is your universe. It is made of what? Only energy. So this is although vacuum, but vacuum can have energy, isn't it? Yeah, vacuum can have energy. Vacuum will not have particles, but vacuum can have energy. This is universe. Okay. Now, one fine day, you remove this part of the energy, and what you did? You brought the energy here, and then you simply shrink this energy to something meaningful, like a dot. I will tell you what is this. The step by step. This is energy. Now, what is left is called dark energy, or simply you can say not energy. This is called actually antimatter because nothing is there, even not energy. This is converted into matter eventually. So the universe is made of only energy which we perceive as a mass. Again, that's very much philosophical. So whenever the antimatter will meet the matter, what will produce? Again, energy. So matter is a condensed form of energy. You can think that. And the day matter will meet the antimatter, what will become? A complete annihilation and energy will be born out of it. So the entire universe is filled with mostly dark energy. I mean, no one knows what is that energy. And dark energy follows the reverse process as the process which we know. So, like we have something called the Big Bang theory. You might have heard about this in class, some other class, I don't know, which talks about the expansion of universe. But the Big Bang theory only talks about the expansion of the matter part of universe, and the dark energy is doing the reverse phenomena. So we really do not know whether the in total universe is expanding or not, because they exhibit a very opposite characteristics. So now again, these are something about the cosmology. We have separate branch in physics, cosmology, in which you can study about the matter, antimatter, and dark matter. There are three aspects of it. And what Einstein was trying to correlate is that do not say the mass as something exclusive thing in the nature. What he was trying to explain that mass is simply a form of energy, and that's why he said that E energy is mc square. This is the conversion formula. In a way, you can think about this. In fact, every energy. uh, So, in fact, every energy becomes an equivalent mass of this value. So, if I ask you what is the mass of photon, you can say roughly it is h nu by c square. Because something with energy will have equivalent mass. Now, which mass is this? Rest or relativistic? Which mass is this? Should we say rest mass or should we say relativistic mass? Which one?
Relativistic.
Exactly. This is relativistic. Why? Because we started with the basic assumption that photons are having zero rest mass. So this way of defining mass is called relativistic mass. So everything having mass. In fact, the mass was calculated. It came out something like 10 power minus 42 kg. I mean, theoretically. And imagine this number 10 to the power minus 32. You know the electron mass is roughly 9.1 10 power minus 31 kg. Then, if you divide this by 10 to the power 11, and 10 power 11 is how much? This is 10 power 6 is the million, right? So it's like 1 lakh million. Well, that's something, or 1 million lakh. If you divide the mass of electron into these tiny parts, then probably you will get a mass of the photon. And that is something as good as saying no mass, because these numbers are easy to write but difficult to comprehend. Like you cannot realize how small is this number. I mean, it's just you cannot realize. It's like if I say that a sand particle in a football stadium, then this ratio is not justified because that is still much bigger. If you think the sand particle as the stadium and then think of one more particle there, probably now you can compare how small is that. I mean, of course, don't try it. Brain will burst. Okay, no need to compare these things. These are just numbers. Photons are having zero rest mass, which is like proven. Theoretically, it found to be something very, very small, minus 42 order, and that order is okay to be ignored. Okay. Now I will talk about something more deep about charge. So when I say nucleus or we say nucleons, especially, so nucleons are the particles which are found within the nucleus. we call nucleons. Okay. And what are the nucleons that you know from your chemistry classes? So what we have inside the nucleus? Come on, guys, tell me what we have within the nucleus.
Protons,
Protons and
electrons.
electrons. Wow, I was never aware of this fact. My teacher taught me wrong.
Neutrons, sorry, sir.
Neutrons and protons. Okay. Okay. So inside the nucleus we have only protons and neutrons. That's correct. And can we, if you go inside, let's say you have a journey within the nucleus, can you see that which one is proton, which one is neutron? Okay. The answer is no. So basically, so protons and neutrons are the two fundamental particles which lies inside the nucleus, and later on in the chapter of nucleus I will teach you that these are indistinguishable. It means you cannot really actually see which one is proton and which one is neutron. They don't actually exist as proton and neutron. How they exist is something called quarks. So let's try to understand a little bit of quarks theory. So quarks are assumed to be even more fundamental than nucleons. So quarks are more fundamental than nucleons. Okay. So we have, there are two types of quarks which are found. Essentially two, I mean maybe in advanced physics it's more than that, I think. But we essentially talk about the two types of quarks. We have up quark and we have down quark. The up quark is made of negative charge particles. Sorry, up quark is positive and the down quark is negative. Down is negative, up is positive. The charge on the one up quark is found to be 2/3 of charge on the electron, which you know already. And the charge on the down quark is made of 1/3 of electron. So every up quark is made of this much charge, and down quark is minus 1/3 of charge on the electron. The mass of up quark is less than mass of down quark. So down quarks are heavier. Now don't think much heavier. The difference will be in the some place of decimal beyond your imagination. So on an absolute scale, the difference comes in the 4th place of decimal. They are technically equal. And when you say proton, it is made of 2 up quark and 1 down quark. So what is the total charge? 2/3 plus 2/3 minus 1/3 into E. How much is that? Can you add?
1.
So correct.
E.
So we know the charge on the proton is equals to E, right? We know this.
Yeah.
And the neutron is made of 2 down quarks and 1 up quark. So what is the charge? Minus 1/3 minus 1/3 plus 2/3 into E. How much?
0.
You can see that it is not like the neutron is having no charge. Neutron is having some charge, but some negative and some positive. In fact, if you draw the core of nucleus, I mean core of neutron, the central part of the neutron is positive part, and the outer part is the negative part. Understood? And because the positive and negative are equal, so the total charge is zero. So neutron as a particle, if you want to imagine, this is how you can imagine. It itself is a combination of two charges. So of course, neutron is not entirely uh, neutral. Like no charge is not the concept. No net charge is the concept. And because of this reason, like down quarks are heavier than the up quark, mass of neutron is slightly more than, although equal, but slightly on the bigger side, mass of proton. So these things are important to understand the quantum behavior of nucleus. And because when you enter the nuclei, what you see is the a mixture of up quarks and down quarks. And then we have the, of course, the theory on the nucleus, how they exist, why they exist, and what makes the nuclei unstable, which is a part of radioactivity. So before we study the radioactivity, we have a chapter of nucleus in which the radioactivity is a part of it. And we'll try to understand the phenomena of radioactivity from the theory of quarks. So I just gave a brief like glimpse of quarks so that you should not feel very much strange when I explain this in the chapter of nuclei and nucleus and radioactivity. You should be aware of that things like this also exist, and it gives you some more detailed intuition about how things works in nature. Okay. So when you will study about the like a beta decay and alpha decay, how the decay is possible. So neutrons are heavier, so they when they decay into protons, some extra mass, because I explained you that neutrons are having slightly heavier mass, that extra mass is converting into energy, E equals to mc square by the formula. And that is how this convergence are taking place in nature. And that is why the neutron is capable of changing into proton by switching the quarks. And how they switch? By releasing some energy. So of course, nature is having all sort of energy combinations, and one particular combination gives you the stability and any other combination gives you some sort of instability. So you release energy by switching the quarks and you attain a better stable configuration. So that's how the decays happens in nature. But that is the topic of decay principle, which we will study in the chapter of nucleus. Anyway, this chapter will introduce you to variety of things. Almost this is like an intro to the entire 12th physics. That's why I'm bringing everything in the picture. Okay, so you saw something very basic about charge. Charge was the characteristic, and then we went on to explaining the other characteristics. And now time has come for the thing which you were looking for. What is the J slaves? Huh? Okay, all these things are J slaves only. Now we need to understand two fundamental differences, and the difference is charge and charge bodies. So difference between charge and charge bodies. So it's very confusing for most of the students that what is charge. So I said charge is something which is fundamental, which is like a characteristic. You cannot develop it. So what you can develop? Charge bodies. Okay. So we will not go to the quarks level definitions to explain things. Our discussion will be entirely based on the classical approach, like the smallest entity found in nature which can carry charge is electron, and the charge which it carries is the smallest entity ever found. Okay, and how we came to know about this relation? Anyone knows? It's very famous. I hope you have heard somewhere. So how we know came to know about the smallest entity of charge? The symbol E. E is called the electronic charge, and the value is how much?
1.6 into 10 raised to minus 9.
So how we come to know that this is the smallest value? Anybody? Okay. So there was a very famous experiment. I hope you have
That
heard.
oil drop.
Yeah, Millikan's wall drop experiment. So Millikan never found this value, but rather he found values which were having common multiple. So he found Q1, Q2, Q3, and so on. And he realized that every number, every value can be explained as some integral number of a number, an integer. So there was something common, some let's say x value, and if you multiply x with some number, you can get q1. So let's say x1 gives you q1. Sorry, not x1. Let's say n1 gives you q1, but if you change this to n2, you can get q2 also. So he got that x is something very fundamental, which is the multiple of it is creating all possible charge in nature. So from here he realized that okay, what is the minimum value? So he just with some inspection realized that the x turns out to be a value e, and that was. So every body that we have can transfer charge in this packet. This is the smallest charge that you can transfer, and it was realized that this is carried by a particle called electron, and therefore the charge on the electron is the smallest entity which cannot be subdivided up to J level, which cannot be subdivided. Now we know quarks, but that's okay. It will not affect the fundamental principle, because if you want to define by the in terms of quarks, I can say 1 by 3 E is the fundamental. That's the only difference I need to bring. But let's keep the E as fundamental. And in physics, if something is really fundamental and you cannot subdivide, we call it a universal constant. So E is now the universal charge constant, basically. And the value is the smallest value is 1.6. So any charge that we can develop, we know that we can only transfer electron between bodies, and therefore we can only transfer charge of this multiple, which Raj gives the concept of quantization of charge. So a body cannot have a charge which is fraction of E charge. So E is the fundamental, you cannot break it further. So this is the least charge you can have, and any other charge will be multiple of this charge. Number will be 1, 2, 3, 1 lakh, 1 billion, 1 trillion, whatever, but it must be multiple. So charge we cannot create. What we are creating is called charge bodies. And the charge on a body will be equal to some integral multiple of the charge E. And how it is created? By the transfer of electrons. We know this very fact. Only transfer of electron can create charge. Understood? So every charge that we create is some number of E value. Is this clear? Yes or no?
Yes.
So can we create charge? The answer is
By transfer of electrons.
mhm. Can we create charge?
No.
No. What we create? You can only create charge bodies, not charge. So charge is something already existing. Can you change the charge on electron? Can we tweak the charge on electron? Yes or no? Anybody? Can we change? What is the charge carried by the electron itself?
No.
So that is something fundamental. That is something fixed value. We cannot alter it. So electron is called charge carrier. Electron is not itself charge. Electron is called carrier of charge. They are like some sort of container having charge 1.6 into 10 power minus 19. At the same time having mass 9.1 into 10 power minus 31 kilogram. So electrons are carrier of charge. So when one electron will go away from you, they will also carry that much charge away from you. And by convention, we call electron as negatively charged particles. So whenever they go, the positive is unaffected, negative has decreased, so net will be positive. Understood?
Yes.
So whenever a body will lose electron, it will become
Positive.
positively charged body. And whenever you gain electron, it will become negatively charged body. So are we creating charge or are we creating charged bodies? What we are doing?
Body.
And to create charged bodies, what is the fundamental principle? Exchange electrons. Understood? And electrons are charge carriers, not charge themselves. They do have mass also, but they can carry charge. So this difference is very much clear, I hope so. What we cannot create and what we create, and quantization of charge is meant for what? Bodies or charge particle. Sorry, charge itself. The quantization of charge is meant for charge developed on bodies. It is clear?
Yes.
Now, in how many ways we can make this charge bodies possible? So what are the methods to create charge bodies? See, I have explained we cannot create charge. Let me make it very clear. I mean, just in case if you have any ambiguity, please do let me know, guys. We cannot create charge. We can only create charge bodies. All right. So we are going to learn about something called method to create charge. So the method to create charge bodies. Method to create so what are the methods to create charge bodies? There are three famous methods. First is called by friction, by conduction, and by induction. So we have three different methods: by friction, by conduction, and by induction. and we'll talk about this in brief. So let's start with the first discussion by friction. So I hope you all have heard about the static electricity. So when you rub a comb on your dry hair, it will have the capacity to pull some light, tiny pieces of paper.
Yes.
We all have done this experiment. So now the question is how it is actually possible. So the rubbing creates a transfer of charge. But the question is how rubbing creates transfer of charge. So if you have two bodies, one and two, and if you rub against each other, what will happen? The rubbing will generate heat. What next? Every surface will have some work function. So every surface will have some work function. So what will happen? This work function will be unequal. So one will be lesser, another will be bigger. So what is work function? If you have studied chemistry, photoelectric effect, you might have come across this term, work function. So what is work function, guys? Anybody if can explain? So no one is interested. What is work function? Am I audible, guys?
Sir, how much energy is required to remove electron from atom?
From atom, that's called ionization.
Sir, from a metal surface?
Yeah, that's correct. So in a metal surface, what is surface? In a metal, or for that matter, anything, what is surface?
Anything solid?
No, surface can be for liquid also. No? Water will also have surface.
Oh, yes.
So what exactly is surface? We have a chapter called surface tension, which is meant for water or liquid one. Okay, these are difficult definition. Surface itself is a volume. Do you know? The first 5 to 10 atomic layer of either liquid or solid is called surface. Surface is not the top. It itself is a tiny thickness. But 5 to 10 atomic layer compared to infinite layer is as good as the top. But you need to understand the surface itself means 5 to 10 atomic layers. So I will explain surface. That's interesting thing. So the surface is 5 to 10 atomic layer, and one atomic layer we believe as roughly 1 angstrom. So 10 atomic layer is roughly 10 angstrom, which is like 1 nanometer. So in a macro world, 1 nanometer is big enough. For our case, it is nothing, isn't it? Anyway, so of course the work function is the minimum energy required to remove the most loosely bounded electron from a surface. So what is the definition? Most loosely, because the electron in the 10th layer will have some difficulty to remove, and electron in the 5th layer will have difficulty to remove. the first layer and second layer will be different. And why the layer concept is important, because you will come to know later on that every radiation will have some penetrative power. You might have studied in the class 10th or 9th that the gamma ray is having the maximum penetration power than alpha rays. Okay. So gamma can penetrate much deeper than other rays. Even the visible light having different penetration. So when a light interact with a matter, it do not usually interact with the very first layer. Sometimes it interact more profoundly with the 10th layer than the first layer. So depending on the wavelength, the interaction differs. And the inner layer may have more interaction than the outer layer. Now these things are again why it is important. You will again come to know that in a chapter like a semiconductor, we have optoelectronic devices, which is a part of JE. If you open the NCERT textbook and go to the chapter of semiconductor, you have a topic called optoelectronic devices. And in that devices, you have a topic called solar cell, the solar panels across which we have very much aware of. In solar cell, the visible radiation actually goes much deeper than the first layer, and therefore gives rise to the different, you can say, conducting phenomena. So it is quite possible that such things will have the penetration power of a given spectrum deal with the matter in a different way. So the interaction of radiation and matter is a big topic, and who will interact in what fashion is a topic of interest for many researchers. So these are mostly studied experimentally because you cannot just say it. So there is a blue box in the NCRT. You can read separately about the spectrum and the wavelength versus the penetration and the radiation. And that is something which defines the working of solar cell. Anyway, that's a different story altogether. And but this idea will help you in understanding that how solar cell works, which when I will explain that topic, you all can understand very well. So every surface will have different work function. When you rub two surface, what happens? Heat is developed. I hope you all have explained this. If you don't believe my word, you can rub your cheek, you can feel the heat. Or rub your palm, you can feel the heat. So I expect that you all agree with the fact that the rubbing creates heat, right? So
Yeah.
heat is a energy. Heat is a form of energy. We can say heat is an energy. So when surface will receive the energy because of the work function, they will be able to release some of the electrons. So technically, the surface with lesser work function, the surface with lesser work function will release easily compared to the surface with greater work function. So a lesser work function surface will become positively charged or negatively charged. Can you guess?
Positive.
Yeah, correct. Why?
It will easily remove the electron.
Correct. So the one which will easily or you can say readily remove the electron will have tendency to become positively charged, and the other by virtue of this will become negatively charged, but it will have to accept more than it is able to emit. So it is the work function which decides the positive and negative. So surface with lesser work function becomes positively charged and the surface with a greater okay. So this method is clear. I hope so that how friction is able to create charged bodies. The next one is important. The next one is called biconduction. So what do we mean by conduction? Any idea?
Flow of
Sir, when the bodies touch, the flow of electrons from one side to the other.
All right. So when a charged body is brought in the contact with an uncharged body, right?
yes.
This is what you're trying to say?
Sir, wha- sir,
A charged body should be brought in contact with uncharged body, right?
yeah.
Um, So this was a very famous gold leaf experiment. I hope you have heard about this. Maybe not.
Yes, sir.
So if you bring a conducting rod with some charge already, so having a positively charged rod is like a deficiency of electron. You can just interpret in that way. For the purpose of discussion, I will recommend that you can think the positive charge as the freely flowing object. Imagine these are positive electrons, and negative charge you can think as a fixed object that they cannot move. This reverse assumption will help you in realizing various things. Then I need not to explain things in terms of electron. I can say I can explain things in terms of a positive electron or positron. That so imagine this charge is spread over the rod. Now, if you give similar charge to any body, will they attract or repel? What they will do?
Repel.
They will definitely repel. So at equilibrium, they will try to go as far as possible. So at equilibrium, what will happen? the repulsion will make sure that the charges are far apart as much as possible, because that is the only way you can minimize the repulsion. Now, what is the meaning of touching the another body? In this experiment, you bring a charged body and the other body is uncharged, and you make a connection, you make a contact. What will happen? What this charge will try to do?
Try to flow.
It will try to acquire the surfaces available in order to minimize the repulsion, isn't it? And by touching, you have given the access to the free surface, the surface with no charge. Understood? So let's say you have a school bus. There are two buses. One is completely full and it's too much rush. Seeing this crowd, the management decides to allow one more bus for the same route. What will happen? The moment next bus will come, some of them will get down from the first bus and go into the second bus, isn't it?
Yes.
Why they will do so? Because they have the first thing access to do so, correct? So once you can make a connection, the charge are already under repulsion, and the moment you make some surface available, they try to spread even more throughout the surface, and the repulsion between charge will get minimized in the due process. Understood? So conduction is a process in which charges are spread out actually. And why they spread out? For the obvious reason of minimizing the repulsion, and it was very much well known that like charges repel. So the flap of the gold foil, this is a gold leaf actually, thin gold leaf. So as a result of repulsion, and it's the jar was vacuumed. So because of the vacuum, once charge will come, of course you cannot see charge, but they will repel and they will go far away from each other, which is the proof that now they have equal charge, because repulsion is the true test of electrostatics. Okay. So why conduction spreads the charge? To minimize the what?
Repulsion.
Repulsion. To go as far as possible. It is clear?
Yeah.
But in physics, how we express this? We cannot use the word repulsion in the context I just explained. So there is a way of saying this by a nice name called potential. So we say that the two surfaces having a physical connection, I would say not physical, the electrical connection will keep on exchanging the charges till they acquire the same potential, which is an indirect way to say that till they minimize their potential or energy distribution or energy density actually. So the whole purpose of conduction is to minimize the potential and to not just minimize, to make it equal. And two surfaces at same potential are said to be in electrostatic equilibrium. Just like temperature makes the two bodies at thermodynamic equilibrium, potential makes two bodies at electrostatic equilibrium, which means no more transfer of charge will take place. They will stop. So definitely the potential should depend on geometry of the surface, isn't it?
Yeah.
Let's say we have an auto having capacity of 3 passenger. So an auto with 5 passenger, a bus with 40 passenger, but with capacity 50. Which one will have high potential, auto or the bus? So a bus with capacity 50, but actual passenger 40. Auto with
Bus.
capacity 3, but actual passenger 5. So which one is at high potential, the bus or the auto?
I think bus.
Anybody else?
Sir, auto because they are all cramped up.
Pardon?
Auto because they are all cramped up.
Yeah, of course, auto because it is more than capacity, right?
But I have a doubt in this.
Yes.
So,
Yes.
bus is having capacity of 50, but it has 40. So, like, it has more potential, right, to occupy more passengers.
Potential means, oh, okay, okay.
Isn't it that way?
Wrong way. Potential doesn't mean the ability. Potential means repulsion. So
Okay.
we have the fairly lesser repulsion, right?
Yes.
Okay. So lesser repulsion means less potential.
Okay. Okay.
Do not take it as a like you have a potential to crack MIT, Harvard, IIT. Not in that way.
Okay.
Potential here means the measurement of repulsion, but in indirect way. So of course, potential does not mean bigger potential does not mean you have more charge. It is about the number of passengers and the size of the vehicle. So the number of passengers and the size will together decide the potential. And one thing you can common sense say that bigger the size, what to expect? Less potential or more potential?
Less potential.
Definitely. So let's say if your entire school will go to football stadium, I mean there is no dearth of place to sit, right?
Yeah.
So definitely we can say the bigger dimension will have lesser potential. And of course, if more people will go to watch it, the repulsion will definitely increase. So in a way, it is proportional to charge, right? So there is some inherent relation that it should be proportional to charge and inversely proportional to dimension, which we realize that is actually true. So dimensionally, there is a inversely proportional relation, and with charge, a proportional relation, and that we will study later on in topic of potential. So potential is the indirect way to understand what is repulsion, and every connection which you create allows the charge to move throughout the surface available. Now the question is how much time it takes. Can you imagine the moment you touch the rod to the rod in the jar? What is the time for the charge to flow?
Sir, very less.
It takes just 10 nanoseconds. The process of transfer takes only -8 seconds. It is instantaneous process. There is no delay at a level we think about. Now imagine if we have a conductor. So we have 3 conductors. So you can think as a 3 islands. Now you can see right now these islands are isolated, correct?
Yeah.
So any charge given to, let's say, you can think charge as the like person living on this island. So these all 3 islands are isolated. Now you cannot move from one to other. So let's say by helicopter I drop Q person on the first island. Now the population is too much. It's very much compact. All are struggling. Repulsion is too high. So then one fine day you decide to make a connection with some conducting wire. So what this wire will do? It will give access to the island. So if this is connecting wire, so this connecting wire will give access to this island, and what will happen now? Some charge will flow, and the charge will flow and will also come to this island. And then if I make another connection between this island to this island, you get the access with all three. The charge will again flow, some more charge will flow, which will again flow, some other charge will come here also. And now our island will have some charge. So when this flow will stop,
All has equal charges.
all have equal potential,
Potential.
not charges.
Potential.
So all island will have similar potential. Now what you need to realize, that potential is a property which not defines only charge but dimension, and it is generally proportional to charge and inversely proportional to dimension, the size of the island. So bigger the size, the chances will be very high that it will have lesser potential, and a small size will have more potential because
Big potential.
the repulsion will be more. I will introduce you the other idea of potential when I will teach you, which is like the work done, definition of work done. So the conduction only stops when potentially every body comes to the same value. So what really defines the flow of charge in a connected mass or bodies is the difference of potential. Understood? This is quite simple.
Yes.
You can always think like the water analogy. You can draw the water analogy. It's pretty simple. If I draw two containers, one thin, another thick, and if I fill with the same amount of water, and if you make a connection with some so what do you think? Water will flow from more water to less water, or will not flow? Water will flow, yes or no?
So not flow right at this point.
So you can see clearly that this is having more water, less water, but still they're not flowing because the height is same.
Yeah.
So charge is not the condition or criteria for the flow. What really matters is the potential, which is nothing but like a height. So the height represents potential. Understood? Is this clear?
Yeah.
So if until we do not have the difference of height, flow cannot take place. So imagine a thin tube with water level till here connected with a big tube, water will flow this way, isn't it?
Yes.
Yes.
So water flows from high water to low water, or bigger height to lesser height.
Bigger height to lesser height.
So similarly, the flow will be because of the difference of height, and height is like a potential. I hope this is clear.
Yes.
So always remember, the potential is the reason for the flow of charge. The difference creates the flow, and the equality stops the flow. two conductors at same potential are said to be in electrostatic equilibrium. So let me mention this clearly. Yeah. Change the color. So two conductors are said to be in electrostatic equilibrium if they have same potential. And same potential does not mean same charge. Now, let's say somehow you know or you're aware that two conductors are identical in shape and size. Okay. So you know the dimensions they are equal. So when they will have same potential?
When they will have same charge.
Exactly. So if we have two identical buckets, so they will have same height only when they have same water also, no?
Yes.
But if you are not aware about the dimension, can we comment about the charge?
No.
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 So what you need to remember, we can comment about the equality of charge only when they have same dimension. Okay. So two identical conductors will be in electrostatic equilibrium when they have same charge also. Understood?
Yeah.
I hope this is not very difficult to understand. Common sense. Let me just mention this fact also. So for identical conductors, the potential okay. Oh, I have explained it. So for identical conductors, they will have same. They will have equal electrostatic equivalent when they will have same charge. So the same charge concept is only applicable when you know that the dimensions are equal. Okay. So for conduction, what we do? We bring the two conductors in connection, in contact. So I will mention here. Now, what do you mean by electrical contact? Let's say we have two conductors and we join with some PVC pipe or some plastic. Can we say this? They are connected? The answer is no, because plastics are insulators. Say they may have a physical connection but not electrical connection. So we must have some conducting medium. Then only we can say they are connected. I hope this is clear.
Yes.
So until we do not have the connecting medium, we cannot say they are connected. The medium must have some conductivity. All right. So I hope
Yes.
these are the takeaways from the conduction part. I mean, of course, potential is something we have to learn separately. We'll discuss more about it in the chapter of potential. So the last topic for today will be induction, which is very, very important to understand. And if you understand these three phenomena clearly, friction, conduction, and induction, probably this entire electro will be very easy for you, and especially capacitor, because the most difficult part is understanding the meaning of these basic terminologies. Induction, what we do here? A charge, a charged body is brought in the vicinity, not connection. So vicinity means they do not touch. They are just close enough. All right. So for induction phenomena, what is required is that you must bring a charged body in the vicinity of an uncharged body. So let's say we have a charged body. So this is the charged body. Let's bring the uncharged body. So we will take the case of conductor. That will be easy for you to understand. So what is the feature of conductor? Like how they are so special? In what sense? So a conductor is recognized by the ability to conduct free electrons, right? So conductor is a medium, unlike other insulator. Conductor is a medium with inexhaustible supply of free electrons. I mean, it will never end. Whatever you want, you can get for all practical purpose. So what do you say? Conductors. So these free electrons are actually free. They can move right and left. So the moment you bring the positive charge, what will happen? These electrons will have the natural attraction towards the positive charge. So as a result, what will happen?
Sir,
They will
charges will bundle up.
they will start moving towards the body, but of course they cannot go towards body. They have to stop here, right? So some of the electron will come to the leftmost end. As a result, eventually the right end will have the deficiency of electron, which you can represent by plus sign. Okay. So what you can realize that this plus and this minus will attract. But what about this and this? So when you bring a charged body in the vicinity of an uncharged body, what type of interaction is taking place?
Attraction
Only attraction or repulsion?
as well as repulsion.
Correct. So uncharged and charged body will attract and repel both. So what we can say? Uncharged and charged body but which force is dominant, attraction or repulsion?
Attraction.
Attraction.
Common sense. So the net force is always attraction.
Yeah.
It is generally asked in the examination that and charge and uncharged body, do they attract, repel, or do both? The answer is they do both. But if the question is a charge and uncharged body, the net force will be. So the net force will be of attractive nature. Okay. Is this clear?
Yes.
I will give you a basic idea about something called grounding. So what is the ground meaning of grounding? So let's say we have same situation. Quickly, so when a charged body is brought in the vicinity of uncharged body, so what happens that this plus and this minus gets bonded together. You can think like something like lines of force. You might have heard in magnetism, something like magnetic lines of force. So similarly, we have something called electric lines of force. And every positive and the nearby negative are kind of bonded together with this invisible lines, which you cannot see. But they are like holding hand to each other with this invisible hand. You cannot see it. But the outermost, the farthest charge is having no such relation. The moment you ground means you connect with earth. So it is like you are hypothetically connecting to the earth actually. So ground means you make a connection from the object to the ground. Yeah, that is how we think. Now technically the earth is assumed to be at a zero potential. Why? Dimension is infinitely large technically. And what I
Yes.
told you that the potential is something like a charge upon dimension, because dimension is so large that eventually potential tends to zero. So technically, the earth will maintain the potential to zero value no matter how much charge you give it or take it. The reason is simple. It's huge in size, and therefore it will maintain zero potential. So connecting a body with the earth is like giving access to the universe. I'm saying that go and sit anywhere in the universe. No repulsion, no potential, zero potential. So what will happen as a fact, because earth is called the infinite charge reservoir with zero potential. So no matter what charge you give or you take away, it will not affect its potential. It will remain zero. So looking at the deficiency, the Earth will, it's like Mother Earth. Mother is always helpful. She will supply some electron to make this or replenish this positive charge. So that electrons will come to neutralize this portion. Understood? So now in the due process, something happened. What happened? This conductor now will have negative on this side, but no positive here. Why? Because it is now ground. Understood?
Yeah.
Is this particular, guys?
Yes.
So now this is the excess charge, no? Because this was actually the rod was electrically neutral because the negative on the left side and positive on the right was equal. Now whatever Earth has given has become extra. So the moment you make the connection, or you can disconnect from the Earth, this extra charge will remain with you. So once I remove this, and once you disconnect, the conductor will have a net negative charge. So this conductor now will carry some negative charge. And in the absence of other conductor, it will spread uniformly. So this is now a charged body, and this charged body will develop using the process of induction plus grounding. Okay. So what is grounding? A method to give access to the infinite charge reservoir, and the potential of the Earth will be zero. Therefore, anything which you connect with the Earth will also become a body with zero potential. Because if that is not the case, then the electrostatic equilibrium cannot be achieved. So two bodies are said to be at electrostatic equilibrium only when they have same potential. Is this clear?
Yes.
Yes, sir.
Not very, maybe you may find this is difficult. I'm giving you maybe some time to ask any doubt from the discussion which we have made so far, because these are the fundamental things which we are going to explore more and more as we delve deeper into the subject. So fundamentally, these are the property of this chapter: induction, conduction, friction, quantization, and that's it.
I have a doubt. Hello?
Yes, tell me.
Can you once again explain about the charge and charge bodies?
Charge is your character. Charge is the fundamental character which
Yes.
you like. Okay. And charge body is that the every body will have equal positive and negative charge, but when you transfer some of the electron, then it is like disturbing the or disbalancing the positive and negative values. So the net value is called charge in a sense that we speak. So in a day-to-day life, when we say charge, we actually mean the net charge. And the net charge, we mean the net charge on a body. In a way, we never talk about charge itself. So the moment I explained the charge in the very beginning as a fundamental characteristic, no one talks in that way. So your communication or your understanding about charge refers to the charged bodies only. And charged bodies can only be made when you transfer some extra electron to and fro, isn't it?
Yes.
So charged body is the body with unequal positive and negative charge. If positive is in excess, then negative, your positively charged. If negative is in excess compared to plus, your negatively charged. Understood? That is very much straightforward. Now, potential depends on dimension because repulsion depends on the separation. So a bigger surface will let you go away from each other. So increase of dimension will also indirectly increase the surface area, isn't it? Can we say?
Yes.
So let's say you take a small piece of metal and you hammer to convert it into sheet. By doing so, do you increase the area? Yes.
Yeah.
So if you put charge on that surface, it will have sufficient space to spread.
Yes.
So we can expect a lesser repulsion,
Yes.
so lesser potential. So can we say bigger the dimension, smaller the potential
Yes.
for a given charge? So you have taken a small piece of metal, you have given some charge. Now keep on hammering the metal piece to make a like a foil. In the due process, the charge will spread more and more and more. Imagine by hammering we are not affecting charge. So at the end of the process, the thin piece of metal will become a big foil. So in such case, the total repulsion will decrease because we have definitely bigger area to cover. So dimension will decide the potential, and that is the whole chapter, which is given a name, capacitance. Do you know this? The formula of capacity is what? Epsilon A by D. Area decides capacity, and we'll come to know that the definition is Q by V. You can see they're anyway having the inverse relation. More the area, less the potential. And of course, it's reverse process. So the capacitance is an alternative to deal with the potential. So every question of capacitor we can solve by concept of potential. The thing is, capacitor as a circuit is a very convenient way to deal with. So that's why we have a chapter called capacitor. Capacitor is nothing something new or something extraordinary coming directly into picture. There is no need to study capacitance to solve any question. But when it comes to circuit, it becomes really convenient to deal with. That's the whole idea. Anyway, any other doubt, guys? Please ask before we wrap up this session. So I hope this doubt is clear. Kanu?
Yes.
So anybody else? Krishiv, Aditya, Manasvi, Mugdha, any doubt, guys?
Or no. Not no.
So we have finished the very first part called the introduction. So what we did today was purely introduction. Of course, this is something that we can omit and start the Coulomb's law directly. But the absence of such premise will make the subject difficult. Now you have more visible idea about what is happening. When I say charge, when I say charge bodies, when I say work function, when I say conduction, induction. So make sure that you repeat this, PDF again and again to keep or remind yourself that these are things which I need to remember. So all right, guys, we'll discuss in the next lecture Coulomb's law. Okay. And
I wanted to ask, when are you keeping that doubt solving for
yeah, so
rotation?
yes. So if you have finished, then you guys tell me, like, are you okay on Wednesday?
No, I will finish it by this week. So
So once you guys say, like, if one or two guys, if you finish just one or two, like not all,
okay.
I will start. So if at least two will finish, I will start. I mean, I'll keep one lecture extra for the doubts and discussion. And also, what I'll say is that, okay, this is the first lecture we finished. Before you come to the next lecture, make sure that you finish the videos which is already there on YouTube. Watch it so that we can finish faster and we can focus more on the numerical solving. So next lecture will be purely numerical solving. So we will be solving at least 10 to 20 questions from SC model. Okay. And erodive also.
Sir, for electrostatics, you are telling.
For electrostatics, yes. So you can watch those lectures. It is already there. And once you watch it there, it's very easy for you to understand. And then we can focus more on the numerical part.
Okay, sir.
Okay, guys, good night. Take care. See you next class on Tuesday.